Hi, the 8.2, the two independent proportions. So question, are P1 hat 100 over 500 and P2 hat 150 over 600 significantly different? So P1 hat is 20% and the P2 hat is 25%. So certainly different, but it can happen by chance because we have not very large sample. So we want to see if this is significantly different or not. So idea is similar. So basically, we can simulate P1 hat and P2 hat. Then we compare the difference the many times. Then we can see this, the 5% difference is too large enough to say significant. But here, from the previous section that we studied that the statistical theory, they can derive the approximate distribution of P1 hat and P2 hat that we don't do the simulation itself. So both P1 hat and P2 hat are approximately normal. So this is the same as the previous section. And the two are independent. So we assume that P1 hat and P2 hat are from the different populations. So P1 hat minus P2 hat is approximately normal. So if two random variables are normal, then independent, then generally speaking, a linear combination of these two is again approximately normal. So we can test the hypothesis of P1 minus P2 is equal to 0 or P1 is equal to P2 if we know the expectation and the variance of this quantity, because we know the shape of the distribution that is normal. Okay, so the null hypothesis is P1 minus P2 is equal to 0, and alternative is P1 minus P2 is not equal to 0. Then basically, we want to know the expectation and the variance of P1 hat minus P2 hat. So P1 hat minus P2 hat is the most important quantity to test this H0, but that we have to evaluate the variability. So we need the standard error. And the expectation of this is clear if null hypothesis is true, because the null hypothesis is P1 minus P2 is equal to 0. So expectation of P1 hat minus P2 hat is equal to 0 under null hypothesis. So how about variance? Variance of P1 hat, that was calculated in the previous section, and the variance of two are just the summation. So this is the variance of P1 hat plus variance of P2 hat, because these P1 hat and P2 hat are independent. So this becomes the P1 times 1 minus P1 over N1, and plus the P2 times 1 minus P2 over N2. But actually, the P1 hat and the P2 hat are unknown. And we can estimate those quantity as these numbers, but that is not the optimal, because our assumption is P1 is equal to P2. So if we use all observations to estimate just one number P, then that is better. So we pool all observations. So we add up the denominator and the numerator and take average. Then P hat, this is the overall proportion. So this is the best estimate for P1 and P2. So using this formula, that we can claim that the standard error is estimated by this. So for one sample test, actually we have the P naught, and the assumption is the P naught is equal to 0.5 or something. So we can directly use that number. But here, we only assume that the P1 is equal to P2, and we don't really know what is P1, what is P2. So we have to estimate P hat, and we have to plug in this formula. So now that we know that this Z is approximately normal 0,1. So if Z is large in absolute value, we reject null hypothesis against this alternative. Yeah, and one-sided test is also possible. And in such a case, the rejection region is only one side of the standard normal distribution. And here is an example. Okay, so just the concrete example. And the two proportions, 100 over 500 and 150 over 600. And the P hat is overall proportion. So 500 plus 600 on the denominator, and the 100 and 150 on the numerator. So that is the 22.73%. So that is the p hat. And so the z is equal to the difference between p1 hat and p2 hat. And this is equal to p hat times 1 minus p hat, and times 1 over 500, that is n1, and 1 over 600, then take square root. Then that becomes negative 1.97. So you can see this is very marginal case. So if we have the 5% significance level, the threshold is 1.96. So we barely reject the null hypothesis. So we reject P1 is equal to P2. So if we have 5% difference with the sample size 500 and 600, then we barely reject the null hypothesis. So this is intuitively so it's intuitively pretty hard to reject null hypothesis. If you really do the surveys with sample size 500 and 600, and if you have proportions 20% and 25%, maybe you want to strongly claim that the 25% is really larger than 20% because the sample size is more than 100. But actually, it's only slightly significant. So the one intuitive reason is that even if you have 500 observations, each observation only have very limited information, whether 0 or 1, whether Pepsi or Coke. So even with a large sample size, moderately large sample size, it's hard to tell if these two proportions are different. So for the binomial results, you really need a large sample size to get meaningful results in statistical testing. And here is the example. Actually, the R implements slightly different and more accurate test. So this is actually the test from section 8.3 and 8.4. But basically, we can use this as if the approximate of the test we discussed in this video. So 100 over, okay, so the format is this, so 100 over 500 and 150 over 600. And then we can test with this prop.test function. And then actually we can test the difference. And again, this is the squared statistic. So this is the z square. And it reports the p-value. And the p-value is 0.057. So last time that we barely reject the null hypothesis, but here we cannot reject null hypothesis. So slight difference in approximation makes some difference. So if you previously we calculated the z statistic as negative 1.97. If we square it, that becomes 3.88. So it's slightly overestimated this squared test statistic, 3.60. And both are approximation anyway. And I think the chi-square test has slightly better approximation, but anyway, both are approximation. So we cannot say a strong argument. And another example. So matriculation rates. This is on the web. This was on the website at Wayne State. So now we don't have this kind of valuable data set for admission statistics for medical school. But okay, so this is the matriculation rate of Wayne State University Medical School in 2009. So applicants and the actual number of students who entered the college, not necessarily admitted. So only a part of admitted students are actually enrolled in the college. So this is the enrollment. So it's not really admitted student, but okay. So you can compare this ratio, the metrics, by undergraduate institution of the medical students. And you can see that if you graduated the Wayne State University, then more students entered WSU, the medical school. So 54 out of 143. From U of M to Wayne State Medical School, only 85 out of 483. So only maybe less than 20%. So we want to see if these proportions are different. And but only we have the small sample size for the binary data. So we are not really sure if we can reject null hypothesis. Okay, so the prop test we can use, and this is U of M, and this is Wayne State, and we want to test. And at first, sample proportion 17.6% and 37.8%, so much larger. And how about the test result? And the chi-squared statistic, this is the z-square statistic. So and this is actually the 24.8, so pretty large. And the p-value, so if we take square root, still 5, so it's large. And the p-value is equal to the 6.3 times 10 to the power -7. So it's highly significant. So we can reject the null hypothesis that the two undergraduate institutions have the same proportion of the metrics. A couple of notes. So the first one is already mentioned. So second one, 95% confidence interval for P1 minus P2 is the negative 0.292 to negative 0.110. So this only includes the negative values. So this means at least the Wayne State University have the 11% the higher the number of students, the percentage of students enrolled. So it also indicates that the difference between the U of M and Wayne State is significant. And the last point, the input can be 2x2 matrix. So originally we put the vector of 85 and 54 and another vector of 483 and 143. But if we put the number of not admitted student, so not admitted, not enrolled students, then we can do the same test with just one matrix. So we have the 55 and the enrolled and the not enrolled. So not enrolled is 398 and the Wayne State 54 enrolled and the total is 143. So 89 are not enrolled. So if we use this matrix, just the input can be just one matrix rather than two vectors.